In this particular segment, we want to look at one of the most important sets of substitution patterns that we can find on benzene molecules. So the first of these, we want to look at if we just have one substituent. So here we have maybe something like chlorobenzene. We just have one substituent. And for reference, we'll just set it at the top. And here is our molecule. And we can put in our high order rotation axis. Now, one thing that I was able to do for this set of molecules is I found labels that have open holes in them, and they're colored labels. So one of the nice things about these types of labels is that as we rotate around, for example, let's say if we have a C6 operation, we can rotate by C6, by a sixth of a turn. Let me get it all the way around there. There we go. So that would be our C6. And by having these types of labels, it's immediately obvious that C6 is not an operation of the group. We can see that orange has turned into green. And we can see this because when we look in the center of the top disk, we see a different color in the center. If we see a different color in the center, that tells us that one of the atoms has moved. It is no longer invariant, and therefore, that symmetry operation is not an operation of the group. So right away, we see that we no longer have C6. Now we can go back to our original arrangement here. And we can try things like C3. So let's try C3. And we see right away, we get our molecule all the way turned here. But I think sticking together is a little bit of a challenge. There we go. So one difficulty of using sticky materials is that they tend to stick to each other. Okay, so that is what happens after a C3 operation. Again, by looking in the center of the top disks, since we see two different colors, one in the center, one on the outside, this tells us that one of the atoms has moved. They're no longer identical, so therefore this isn't one of the symmetry operations of the group. There also will be a mirror plane through the plane of the molecule, as there has to be for a planar molecule. So we can look at some of the other symmetry operations. So the high order rotation axis that we're going to find is actually along the length of the molecule like this, and we actually have a C2. And we can rotate our C2 like that. So we see that we have C2, and we also have a mirror plane. And we can prove our mirror plane by folding over again. When we fold over, we see that the like atoms match up. The green is with itself. So we have, in this case, when we have a monosubstituted benzene, the point group, so long as the substituent is planar, we're going to have point group C2V. So no matter how it's monosubstituted, any monosubstituted benzene will be C2V, so long as the substituent is planar itself. Now, we want to next look at cases where we have disubstituted benzenes. And remember that when we're naming disubstituted positions, we refer to them as ortho, meta, and para, which are of tremendous importance in organic chemistry. As you'll recall, electron-releasing substituents tend to activate the ring, and they will direct ortho and para. Electron-withdrawing groups will tend to deactivate the ring, and they will direct future substituents to the meta positions. And there's essentially one class of exceptions to those two rules. The halogens tend to be ortho-para directors, but they deactivate the ring. So the halogens are a special case of the activation of rings or deactivation of the ring for electrophilic aromatic substitution. So ortho, meta, and para are very important. So here we're going to start off first with an ortho disubstituted benzene. So this might be ortho dichlorobenzene, ODCB. Not ODB, just ODCB. And so let's see what symmetry operations we have with this particular molecule. Let's see if we can figure out what the point group is. So again, we can use our sticky labels with holes in the center to help more easily tell when we have a symmetry operation of the group and when we don't. So again, let's try see if we have our C6. Going to rotate. And we see right away that we have green and orange together, and green and orange over there. This tells us that some of the atoms have moved. They're no longer invariant. We do not have a C6. And what we'll find out in kind of a quick version of this is that if we go through all the symmetry operations of an ortho disubstituted benzene, we still get C2V. So even though it looks different having an ortho disubstituted molecule as opposed to a monosubstituted benzene, they still have exactly the same point group symmetry of C2V. That's a little bit of a surprise to students. So now let's look, having done ortho, let's try meta. So we'll go through the meta series here. And we'll try to line these up. And we can imagine that the green labels refer to perhaps chlorine. So this might be meta-dichlorobenzene. And we want to figure out the point group symmetry here. So again, if we try to rotate by a C6, we can see very clearly, using our punched out labels, that this molecule does not have a C6 operation. The atoms are not invariant when we do a C6. C6 is gone. We've reduced the symmetry quite a bit from that of the parent compound benzene. Again, we will find out if we do all the symmetry operations of the group that meta-disubstituted benzenes are also C2V. So while the chemistry of the molecule will change quite a bit, going from ortho-disubstituted to meta-disubstituted, as far as the point group symmetry goes, they haven't changed at all. They're still C2V. And then we have one example remaining, which is our para-disubstituted. So we can set this up. Again, you can imagine that the greens might be chlorine, and the orange will be the hydrogen. So this would be para-dichlorobenzene, for example. Para-dichlorobenzene is widely used to kill moths. They used to use naphthalene in the old days, but naphthalene is suspected of being a carcinogen. So industry has moved to para-dichlorobenzene, which may or may not be any better. So let's see if this molecule has a C6 operation. So we see that when we do a C6 on our para-dichlorobenzene, that the atoms don't line up. C6 is not a symmetry operation of the group. We will find out that the high order rotation axis in this direction, let's start off back where we were before, like this, is a C2. So we can actually rotate the molecule by 180 degrees through a line straight through the center. Rotate around. We get to the magic arrangement where all the colors line up perfectly. So we see that we have a C2 operation for the para-dichlorobenzene. And if we work out all the other symmetry operations, we'll see that this is an excellent example of D2H. We had previously encountered point group D2H with ethylene, and now we see another example in organic chemistry with a para-dichlorosubstituted benzene. So this is a very, very important example that comes up quite a bit, these disubstituted benzenes, and how the point group symmetry changes as we go from ortho and meta, which have the same point group symmetry of C2V, and then we go to para-disubstituted benzenes, which have a different point group of D2H. The thing also to keep in mind is D2H is a centrosymmetric point group. It has a center of inversion. So therefore, if we were given a pure disubstituted benzene, we could easily determine whether it was para-disubstituted as opposed to either ortho or meta by using vibrational spectroscopy, by using IR and Raman complementary. We would actually be able to determine if we had a para-disubstituted benzene compound. With that done, episode 6, the end of episode 6. So next time, we'll see you for episode 7. Have a good one.